from the DTA image or video. We know the benchmarking or evaluation of flip-flop setup and hold time is very important in digital timing. In addition, the gate characteristics are so different over different technologies or processes. Therefore, we must exercise the flops characterization every time in any different process node. Should we do the same or similar process evaluation in the analog blocks? Yes, we must do it, and I will show what we should do one by one, and hopefully you will know why you should do the process evaluation clearly. Before doing design, you might want to know how much area or floor plan you should assign. So, what was the first process evaluation you need to make? Think about the passive elements for 5 seconds. Correct. The first thing you need to evaluate is the RLC elements, standing for resistor, inductor, capacitors as follows. First, you may apply the resistors for the series front-end termination, biasing, similar law. The unit resistance of the ohm per square would determine the needed physical length and area. Second, the capacitor will be used in the analog filter, CTLE, or the DC feedback loop. Therefore, the pole 0 or the bandwidth will determine the required area from both the unit size of the resistor or capacitor. In addition, the capacitor is a good decoupling or bypass with low impedance for the supply integrity improvement in the high-frequency supply noise ripple. How is the requirement of the inductor? Bingo! The inductance may depend on the geometry of stack or top spiral routing, but the parasitic capacitance and resistance may impact on the self-resonant frequency and the quality factor. Therefore, you should see the inductor characteristic would differ a bit from process to process. Even though looking at the same 28nm process, you may still choose the different metal stack and get totally different inductor characteristic. For example, a higher metal stack with a thick top metal would have a higher quality factor in a less resistive loss for inductor, which may improve the phase noise of any RLC PL for the series clocking. Similarly, a high quality factor capacitor in an RLC tank will also improve the PL's phase noise. A less parasitic capacitance of the inductor will also increase its self-resonance frequency to operate at a higher data rate. Therefore, the RLC image should be clear to you about the area or floor plan impact among different process nodes or even different metal stacks in the same process node. Do we have other things we need to consider for the passive RLC? Think about the temperature images for 5 seconds. Yes or no? For the PVT image, the passive device should not have much to do with the voltage, but the technology or the temperature may have some variations. After discussing the dominant factor in the process node, the temperature would have the second impact over different processes. For example, the resistance would have the temperature coefficient. Some processes have a big variation from minus 40 degrees C to 125 degrees C, but some process nodes would have a smaller temperature coefficient temp call from minus 40 C to 125 degrees C. Similarly, the quality factor of the inductor or the capacitor would have temp call. Even for the inductance or capacitance, you should also watch out for the temp call if you are working on a precise oscillation frequency over PVT. What else should we look at carefully for the passive RLC? Think about the fabrication images for 5 seconds. Great, we discussed this before in the white RCC video, which shows the resistance could vary plus minus 20% from nominal value or plus minus 10% depending on the process node or fabrication ability. Similarly, you should also see the similar variation in the inductance and capacitance from wafer to wafer. Besides the global variation, what else should you pay attention to? Think about the local variability for 5 seconds. Bingo! The local variability may have a big impact on your block if you are applying the passive RLC for the matching. We've known the absolute value vary a lot, and that's absolute quantity. For example, gain isn't a good design. For high precision specification, we can use the ratio of any two passive RLC to achieve a high precision gain instead of its absolute value. A very simple example from the Microelectronics 101 is the common source amplifier. Even if the GM of the active device is ideal, the gain of the GMR will vary plus minus 20% of this. For example, if you put a source degenerated resistor at the source of the transistor, then the gain would be the ratio of RD over RS, which would have a much higher accuracy or much less variation than the 20%. If that's the case, why should I bring it up? Think about the high precision requirements for 5 seconds. Correct. If you are targeting a high resolution or precision, the target should be somewhere around 10 bits or even 14 bits. Unfortunately, it's very difficult to minimize the local variability easy unless we've done a special dynamic element matching in the YDEM video. But before the design, you should start with the Monte Carlo simulation from the foundry model to figure out how bad it is if you don't do anything with it, such that you can have a better understanding of the bounded performance. So, the RLC process evaluation should help you when you start your new design block from scratch. Hopefully, you already agree with those ideas, but do you think if you even benefit from it in the old design block? Think about the porting image for 5 seconds. Great. When you plan to do the porting from one process to another process node, you must understand what the passive characteristics are before deciding the next process node. Could you tell me why? Yeah, a simple answer could be the area might be bigger than what you will target in the next ported process node because of the smaller resistance and capacitance in the next process node. Therefore, in exactly the same design parameters, you must increase the area and redo the floor plan, which could be a big issue. If you are porting from 28 nm to 40 nm, that should be the case and no surprise. But if you expect to port 20 nm in foundry A to a 20 nm foundry B, you might not expect this happen. Unfortunately, this could be the case. Therefore, you can decide if choosing the foundry B is the best for you between the porting effort, layout schedule, and the wafer price. Besides the porting effort, what's another motivation for you to choose the RLC process evaluation? Think about the PDK images for 5 seconds. Correct. The process design kit PDK will keep updating from the foundry, since their process verification will also update because of several reasons we are not sure. Therefore, it's likely the PDK has been changed during your porting phase, which could impact area, floor plan, temp call, precision, etc. Another possibility is that the PDK could change after you tape out over different wafer in time. Then you could have a big picture how the impact is and contact with the foundry if there's anything you could do or expect for the change based on the furthermore simulations. On the other hand, you could check the updated PDK and find that the change is little, and then you can relax with no need to run any simulation. So, the RLC process evaluation is a good spark check for the PDK update. Here are a summarized image showing you why the process evaluation for the RLC passive elements is a must, especially in your first day of the design phase or even the first day of your project planning phase in choosing which process you would like to go in your new project. If you are doing the new design from scratch, the estimated area of the RLC can help you decide if your service topology is reasonable to implement in an amplifier, biasing, passive filter, and LC tank, etc. But to achieve the good power integrity, signal integrity, and low jitter target in the first day or the first week kick-off meeting, then those evaluation data should help you optimize your design during the troubleshooting or improve phases to make your design more reliable over PVT consistently in a good QA maintained phases. In addition, the high precision requirement may need your passive matching idea to provide the best design exercise like DEM to improve the reliability and consistent accuracy from wafer to wafer and chip to chip during different operating voltage and temperature. What's more, correct, if you plan to pull the existing design from one process to another process node, you must understand what the passive characteristics are before deciding the next process node. For example, you must make sure the smaller resistance and capacitance in the next process node, which you made the right decision. Otherwise, in exactly the same design parameters, you must increase the area and redo the floor plan, which could be a big issue and usually occurs from advanced node to an older process node. Also, you might port the same process node in different foundries. Therefore, you can understand if choosing the foundry B for the new process is the right decision for you to between the porting effort, layout schedule, and the wafer price. Lastly, the process design kit PDK will keep updating from the foundry, since their process verification keeps changing no matter little or big changes. Therefore, it's likely the PDK has been changed during your porting phase, which could impact the layout, floor plan, area, tempo, precision, etc. Another possibility is that the PDK could change after you tape out. Then you could have a big picture of how the impact is and contact with the foundry if there's anything you could do or expect for any change based on the further simulations. On the other hand, you could check the updated PDK and find the change is little, and then you can relax with no need to run any further simulation. So the RLC process evaluation should be a spot check for the PDK update. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and place your comments down below. Lastly, please share the video link with the people who may be benefiting from it.